Welcome to the world of calculus. Today, I'm your host, Hirsch Seth, and these are my companions, Joseph and Amormio. Welcome to the pool party.
Let's go! Oh, she turned over.
Today, we'll be talking about concepts of rate in and rate out calculus problems and the uses they have in real life. Now, I'll pass the rock to Joseph, and he will explain what rate in and rate out in calculus is.
So, what is this particular calculus problem? Well, generally speaking, rate in, rate out problems in calculus are found in FRQ problems where you will have to find various different things. Some of these concepts that will be included in FRQ problems will be: pause this video if you need to take any notes of this. Now, Amormio will show an example that we made of what a rate in, rate out problem will look like.
Alright, imagine you're designing a pool as you're getting ready for the scorching summer. As you're designing the pool, you customize how much water flows in and out of the pool. To prevent contaminated water, you also design a filtering system which will drain out water and pump back in some new clean water for your pool. Okay, so here's a problem. The rate at which water flows into the pool is modeled by the function h. The rate at which the filtering system takes out water and then brings in the cleaner water is modeled by the function L. At time equals 0 hours, there is about 45 cubic feet of water in the pool. Question 1a asks, how many total cubic feet of water is in the pool in the time interval 0 to 5 hours? Question b asks, what time is there least amount of water in the interval from 0 to 5 hours? And question c, the pipe can hold 150 cubic feet of water before the water starts leaking out of the pool. When t is greater than 5 hours, the water continues to come in and out of the pool until the water in the pool begins to overflow. Alright, pause this video if you want to try solving this problem by yourself.
Question 1a asks, how many total cubic feet of water is in the pool in the time interval 0 to 5? So, we are given three functions. So, h of t is a function that describes the rate of the water going inside the pool. And then L of t is a function that describes the rate of water going outside the pool. And then at t equals 0, there's 45 cubic feet of water in the pool. Now I'll answer 1a. Alright, so first let's start off by making an equation. S of 5 equals S of 0, which is the initial amount of water inside the pool, plus the integral 0 to 5, h of t, which is the amount of water going inside the pool, minus L of t, which is the amount of rate of water going outside the pool. So h of t minus L of t gives you the amount of water that's in the pool in the interval from 0 to 5. So when you plug this into the TI, you get 169.179 cubic feet. Don't forget to truncate your answer to 3 decimal places.
Now we'll answer question 1b. What time is there least amount of water on the interval 0 to 5 hours?
Oh my God, bro.
Oh, hell no, man.
Now let's explain the problem. What time is there least amount of water on the interval 0 to 5 hours? Now, if you do calculus, we know that this is basically asking for the absolute minimum over the time value 0 to 5 hours. And to do that, we need to be testing the endpoints and the critical numbers. Now, the endpoints are already given as we have 0 to 5 hours. And to test for critical numbers, we have to derive the original function and find out the time value that gives us a potential point. Now, the amount of water is already given by this equation, and all we have to do is derive it. Once we derive it, we just have the function that is the rate of water going in minus the rate of water going out, make it equal to 0, and we put that into the numeric solver on our TI-84, and that will give us a time where the value will be 0. Now we got 4.0937 hours, which could be a point where the water is the least amount. And so we plug these back in over to this equation, replacing the t value with our given time values 0, 4.0937, and 5. And we see that S of 0 equals 45 cubic feet, meaning 45 cubic feet of water in the pool at time 0 hours. And compared to these, S of 4.0937 and S of 5, this is clearly the least amount, giving S of 0 equals 45 cubic feet, the least amount of water during the time interval.
Now I will solve question 1c. The pipe can hold 150 cubic feet of water before the water starts leaking out of the pool. When t is greater than 5, the water continues to come in and out of the pool until the water in the pool begins to leak. What t value does the pool begin to overflow? Here, we know that the pool can hold 150 cubic feet of water, and so we have to make the 150 cubic feet of water equal to the original expression that we have. So, and then you have this equation right here, and then you just input that into the numeric solver, and we try to find the t value, and we get t equals 5.513 hours when the water overflows from the pool.
Here's the proof for the fundamental theorem of calculus. Imagine you have a triangle with a base of 5 units and a height of 5 units. On a coordinate plane, the hypotenuse of the triangle is modeled by the function negative x plus 5. Now, how do you prove the area is 25 over 2 units squared using the fundamental theorem of calculus? First, let's explain the fundamental theorem of calculus. Taking the integral of f of x, in our case, it is negative x plus 5 from a to b. In our case, it is from 0 to 5 on the coordinate plane. You will get f of b minus f of a from the integral of f of x from a to b. And integrate negative x plus 5 from 0 to 5, you will get 25 over 2, just like the answer for the area of the triangle, using 1/2 base times height.
Now I will be talking about the history of the fundamental theorem of calculus. The fundamental theorem of calculus is a result in calculus that consists of 2 parts. The first part was formulated by Isaac Newton and Gottfried Wilhelm Leibniz independently in the late 17th century. The fundamental theorem of calculus establishes a relationship between differentiation and integration, stating that if a function is continuous on a closed interval and has an antiderivative, then the integral of the function over that interval can be evaluated by finding the difference between the antiderivative evaluated at the endpoints of the interval.
Welcome to the world of calculus. Today, I'm your host, Seth, and
Cut it.
welcome to the
Okay.